So we have only 10,000 images, but it's definitely pretty slow on my CPU to run this thing. So how do we make this thing go faster? Well, what I'd like to do is perform as much at the same time as I can. You might be familiar with the fact that on your computer you have multiple so-called core, and these are separate processing units. And so if you're able to, you can do, if you have 8 processors, there's 8 things you can do at once. Now, I mean exactly at the same time, not simulated at the same time, which is more of what we computer scientists would call concurrency. I'm talking about actual parallelism here. So let's take a look. I borrowed this image. It was a decent image, so I pulled it across. It wasn't exactly what I was looking for, but so a processor has RAM, has memory associated with it, and it's got processing units. And the ALU stands for arithmetic logic unit. So this is and it's not really simulating multiple core, but we can think of it as that. So my computer here has, I don't know, 8 core or something like that. And it's got a bunch of memory. And so this operates on this memory here. Now, I could also use something called a GPU, a graphics processing unit. And this also has RAM associated with it, memory, but it's got a lot more processors. And it's actually got a lot more than this. And these processors operate on this data. But every time you see one of these green blocks, it means I can do a piece of the problem. So imagine in your mind overlaying a matrix on top of this, a matrix that's, whatever that is, 10 by 20. And now if I want to add 2 vectors that are exactly the same size, I can add them in one operation, because if I have 10 by 20 matrix and 10 by 20 processors, each processor has to do just one addition or multiply or whatever I'm doing. And so in the time it takes to do one multiplication or addition, I can multiply or add matrices of the same size if I have that many processors. Now, of course, if I have, 100 by 200, then each processor has to do 100 operations, but that's okay, 10 by 10 extra. The point is that I've broken up a very large matrix arithmetic problem into, let's say I have, 200 processors here. I've divided it into 200 sub-problems. Now, of course, what this means, though, is I load data in our standard Python using, read CSV or something, and that goes into the RAM associated with the processor. And I create a model over here as we've done before. To make it execute in parallel, I've got to get it over onto the GPU. And so this is just an extra step, an extra concept we need to keep in mind, that we're going to be moving things back and forth. So when you see me say I'm moving something to the GPU, there are devices, one for the CPU and one for the GPU. It's called CUDA, which is the name of the programming language that we use to program these GPUs. But you'll see me doing the to function to move it to a particular device, because I have to manually say, hey, send this over to the GPU. And if it's computed over here, I often will say, oh, bring it back over to the CPU so I can print it out. So when you see those functions that are moving data around, that's what I'm doing here. So that CPU will bring it back. The other thing to keep in mind is just generally true. It's not necessarily associated with the GPU, but when you see me doing a .detach, what I'm saying is take the model parameters that I'm trying to optimize and detach the gradient component. The gradient component, remember, when I'm doing all of that loss dot backward and all that kind of stuff, there's not only data associated with these model parameters, but there's all of the gradient and the associated computation graph associated with it. And sometimes I want to just get rid of all that stuff. It takes a lot of memory. And so when I do a detach, that means I'm just getting the data component out of it. And if I need to also send that back from the GPU to the CPU, then you'll see me do a sequence of things. Unhook it, and then send it back to the CPU. And I might even then say, oh, and by the way, get it out of a tensor and move it into a NumPy thing. So you'll see a lot of these bookkeeping functions, and they're just something you have to get used to. Now, I'm not sure why. It's probably a marketing reason, but CUDA is not supported on the AMD chips that are in your Macintosh. So I have an iMac, whatever, and it's got a GPU in it, just like most computers, but I'm not able to use it from PyTorch to do things in parallel. Now I've got multiple cores, so it's going to try to use those on the CPU, but it's not going to be nearly as fast as a GPU. However, as we'll see in a second here, we can run this in Colab. In fact, I'll get this into another window for use in a second. Okay. Usual support code, except now I'm going to do something that this is just a pattern I use so that I don't have to change my code. If I'm running on a CPU or running on a GPU, I don't want to have to change my code because I haven't fundamentally changed what I'm trying to accomplish. I'm simply moving stuff to a different device. And so my typical coding pattern is to create a variable called device. And I'm asking PyTorch to get the device object associated with whatever, see if CUDA is available. If it isn't, then I'll resort to the CPU. But then anytime I want, when I'm creating my tensors that I hope could work in parallel, I tell it, hey, go to the device. Now, if on the CPU, well, it does nothing because you're already on the CPU. But this gives me the opportunity to take the same code and run it on a GPU-based machine, and then it will just run, hopefully, it'll run faster. Okay, so this is a little bit of a different bit from our support code. Then I've got the usual plotting functions that we saw before, as well as the grid display. Exact same code as before. I'm downloading all of these images. Got the same size, 10,000 test images and feature size. Shuffle it, and it's like this guy. I'm doing another random sample. Yeah, so for example here, some people draw a 1 like this. So that's why you can get some confusion. All right, so here's our first bit of difference with the tensors. So instead of just saying, I want a tensor, a floating point tensor, I'm saying, by the way, also move it to the device where I'm going to do the computations. And I'm doing this both for the X and Y case. So that just says where it resides, but Python hides all that from me so that I can still do this train test split stuff and get my X and Y training and test data. Okay, so remember, we're solving the exact same problem, so you would expect our model to be exactly the same. I've got a layer of 50 neurons, and because it's a K-class problem, I've got K linear units on the end, and then I'm going to run a softmax on that to get the individual probabilities for each class. But I also, because it's a chunk of data, and I want it to run and be available on the GPU, because remember, I'm updating the model parameters on the GPU, assuming I have one, then I'm going to put that 2 device on there. So this is something that we haven't done before either. Other than that, though, the training is exactly the same. Cross entropy for the general case, I'm just sending stuff to the model. So all of this move it to the GPU stuff, once you indicate that to PyTorch, you're fine. The training loop is going to be the same. So I don't want to have to change my algorithms based upon where it's computing things. I want a layer of abstraction, and that's what PyTorch gives us. Okay, so that's the exact same training loop that I had before. And on the CPU, this takes about 20 seconds. So let's see if we can get a visceral feeling for how this works. 20 seconds is not horrible. Let's run this, make sure everything is okie-dokie. Okay, and notice this little meta command here for Jupyter Notebooks. This will give us the wall clock, the time for executing this thing. So I'm doing 1,000 epochs, and that's 1,000 iterations, trying to compute the loss function and update the gradient based upon the entire training set all at once. Okay, so then you can see that it gave us information. This output here comes from this percent time thing. Okay, so we get about the accuracy that we had before, but this, and just for fun, commit that. Now let's run the exact same thing on a GPU, and the way I'm going to do that is to go over to Colab, and all I did was click on that, and if you have an account in Google, this is easy for you to set up. I'm going to refresh just to get my latest changes. Okay, so first thing you do, there we go. You go to change runtime type. So if you run it without a GPU, it's not going to go nearly as fast, and it'll be on some slow CPU, not like the 4 gigahertz processor I've got on this Mac. So anyway, I set it to use a GPU, and then I go back up to runtime, and if I want, I can say run all. And I'm going to do this one at a time. It's very similar to a Jupyter Notebook, yes. So you just run anyway. It's just warning you. It's very similar to a Jupyter Notebook. I find it different enough to be frustrating, but that's fine. So now notice that it says my device is CUDA, whereas before it said my device is CPU. So now the same code that I had before is going to move everything to the GPU. There's my plot routines, load some data.
Hi, Professor. Yeah. I don't think the correct screen is showing right now.
Does it look like GPU?
It's on the image of the difference between a CPU and a GPU right now.
Really?
Yeah.
Huh. Wow. This browser is not...
I have your notebook. That's weird.
Oh, really? So you should be seeing the Colab notebook right now. You're seeing it, Chris?
Yeah.
Oh, okay. Evan, are you sure you're not? It should. You see this little CO at the top, Colab? Evan, do you see it?
I'm seeing the Colab too.
Huh.
Strange.
Evan, maybe drop out and come back in.
Yeah, I'm going to try that. Thank you.
Okay. Okay, freaked me out for a second there. Okay, so I've got a random set of images, and we'll wait a second for Evan to come back in. And so now I'm moving my tensors to the GPU. And just for fun, let's see what it says if I ask it about why. Let's finish. Okay, so that's not what I wanted. This guy. I don't know how to use this thing. Pulse code. Let's ask it about why and just see what it says. And it tells us where it's currently residing, okay? So if this were on the CPU, it would say device equals CPU. Okay. Okay, so I just want to show you the difference in speed. So we get our model, I push it to the GPU, my training loop is the same, and now I'm running it. And now look how fast that is. It's done in 2 seconds. And that, ladies and gentlemen, is the difference between a GPU and a CPU. So let's run this again. Get my model. The reason I have to get a new model is because I want all those parameters to reset and start again. Otherwise, it'll keep training from where it was. Okay, now, once again, I'll run it. And it's like, oh, so slow, so slow. But when we go to this again, let's make sure we get a new model. And now watch how fast this is. Okay, so we're more or less going to get the same result, except we're going to get it a lot faster. Sometimes you get, if you're not paying for it, they don't give you a good GPU. You get kind of a cruddy one, and you can sometimes tell. but hey, it's free. So that's a big difference. And that's like a 10x speed improvement. And arguably this is a small model, but not too bad. So that's more or less what I wanted to show you about the GPU. It's the exact same problem I just solved with the K-class MNIST thing, except now I've tweaked the code so it's more general, slightly, and I've specifically said move the model and the tensors over to the GPU, assuming I'm running on a GPU. But the same code runs exactly the same both places. So if you guys want to try it, you try it in your CPU, and then you click on this, and it'll take you to Colab and open up my repository notebook, and then you do that thing where you say runtime, change runtime type to GPU, and then you can just do run all. And it's a very similar thing to a Jupyter notebook. Okay, so yet another concept. Check. Questions?